We are just about at the end of our coverage of lossless compression techniques. In the next lecture and lectures after that, we're going to be talking about lossy techniques. But there's this one topic I have left to talk about that is a really big deal in lossless compression. And although I'd like to talk about every lossless compression scheme ever to have existed, apparently your tuition dollars and patience only cover a finite number of lecture hours, unfortunately. So instead, I want to cover this one last thing by way of a broad overview. I will present a detailed example of one scheme that is often used that implements an adaptive approach, but otherwise I mostly have to give an overview because there are just so many doors I have to leave open here. There are so many ways that adaptive methods are a big deal in compression, but we weren't quite equipped to see them or appreciate them until now. What I also want you to think about as we go through this lecture, as we prepare to leave lossless techniques, is about just how many of the facets of these adaptive methods sound similar to LZW, which was the very first lossless technique that we covered in detail, and one that I think we can all agree is pretty primitive by modern standards. And yet many of the things that LZW did, so for example, keeping the decompressor synchronized to the compressor without any overhead, the use in the ancient Unix compress tool of that reset marker, that special symbol, a lot of things like that have actually propagated through many of the techniques that we've seen since, and they show up again today. They bubble back up to the surface. So where we left off in the last lecture was talking about arithmetic coding, and mostly this lecture follows on from 2 lectures ago, not from the last lecture, because we don't need to worry too much about the implementation details as far as the techniques in this lecture are concerned, because if we choose to use an arithmetic coder as part of our adaptive method, we now know that we have a way of implementing that. Okay, so here's a set of probabilities as usual. And we know that arithmetic coding generates a very efficient encoding using only these probabilities. So we don't really do very much pre-processing besides generate that set of cumulative probabilities, or we could use cumulative frequencies. Contrast that to something like Huffman coding, which has to do quite a bit of work before you start the encoding process. And so as we encode every symbol, we narrow down our probability range, and then we encode the next symbol inside of this narrowed range. And the way we've been working with arithmetic coding so far, we have this set of cumulative probabilities that we've computed in advance. So for example, A goes from 0 up to 0.47. And then at every step when I zoom in, so here I'm zooming in on the B's, all I do is scale that original table into my new interval. So no matter how much I narrow low and high, I'll just end up scaling my original cumulative probability table or cumulative frequency table into whatever interval I end up with. So the relative size of the subinterval for B is going to be the same at every step, just scaled into a smaller and smaller window. So that is to say, I guess if A has 47% of the real estate going in, A is going to have 47% of the real estate once I'm done zooming in. So the BA portion of the B range will be 47% of the B range. Now, as I mentioned a minute ago, arithmetic coding is sort of nice because I don't really require much structured, this is a strange way of putting it, structured data or pre-processing. Computing those cumulative probabilities is pretty easy. And in fact, maybe we can prepare ourselves for the revelation that if I want to adjust them, if I want to change them, that's not so difficult either. Now, Huffman coding is often faster in an aggregate sense, so I've mentioned before that arithmetic coding has a bit of a speed problem. Huffman coding requires more work in advance because I have to come up with an encoding for every symbol. So let's say A is 0, and B is 1, 0, I guess we'll make one more, C is 1, 1. But as I've mentioned before, once you have that encoding table, actually generating the encoding is really easy. So if I have AA, B, C, A, all I have to do is for each symbol, look it up in the table. Now compare that to arithmetic coding, where I don't do any pre-processing besides computing those cumulative probabilities. But then once I want to actually encode the sequence, I have a decent amount of work to do at each step. Not just in terms of the set of arithmetic operations, but also understanding that those operations themselves can actually be quite time-consuming, as we saw over the last couple of lectures. So here's a question. Given the relatively low startup cost of arithmetic coding, given the fact that all I need is that cumulative probability table, which is a pretty tangible artifact, something that I could modify pretty easily and maintain whatever invariance I need to maintain. So for example, that all the probabilities are between 0 and 1. Given the low startup cost, why do I have to use the same probability table at every step? Now, one really technocratic response to this would be, well, because we decided to view arithmetic coding, to derive that algorithm through the lens of entropy coding, where so far in the course we've thought of first order entropy, which is to consider every symbol as being independent from all of the other symbols and sampled from an identical distribution, and therefore the probability of each symbol is literally the same at each step. If I read A, B, A, and then I ask you what's the next character, the probability that that character is an A is exactly the same in the lens that we've been viewing entropy coding through as if I see B, B, A, C, and then a blank, and then ask what the probability of the next character is there, assuming that both of these are part of the same overarching sequence, that is, they are drawn from the same distribution. So that's why we use the same probability table. It's for a good reason, but maybe we've buried ourselves a bit too far in theory land there. We know that in practice, we don't generally work with input sequences where all of the characters are independent. And I've said over and over again since lecture 7 that all of these assumptions of independence are important for us to reason about things like entropy and information content, mostly entropy or first order entropy, and to be able to leverage things like the bound that we can set on the ultimate average number of bits per symbol with that assumption of independence. But I never said that we're going to actually deal with independent data in general. Maybe we do our best to make our data independent, so we've got more of a reference point if we want to employ those bounds. But in general, we're going to have dependencies in our data. So this question actually attacks that in a certain way. Maybe it's not obvious how, and part of this lecture involves sort of unpacking the different facets of this question. So every iteration of arithmetic coding is basically independent. I mean, that is, at the beginning of each iteration, I start with some value of low and some value of high. I don't really care how I got there. In fact, really, from the point of view of the encoding process, if you're performing arithmetic coding and I tell you, hey, start at iteration 7, and by the way, here's your low and here's your high. If you start right there, you probably don't even know what previous characters I processed. All you know is that that's low and that's high. You have no idea how I got there, nor do you care. All you care about is how do I zoom in on the next iteration. So from that point of view, if I can come up with a good reason to do this, there really isn't any problem with changing the set of probabilities that I use. If I tell you to start on iteration 19 or iteration 74, and I hand you a probability table, you don't really care whether it's the same probability table that I was working with before, up until that iteration. In fact, I could change the probability table at every single step. Subject to one obvious caveat, which is that I need this process to be reversible. So if the encoder is going to change its probability table, obviously there has to be some way for the decoder to know what's going on and to do the same thing. But supposing that I could ensure that that's going to happen, there really is no problem with arithmetic coding changing probabilities at every step. And of course, as I said, the reason that we've been using the same table at every step is based on a bunch of assumptions that were made in the service of some theoretical things that we were working on, like some entropy stuff. So working with the bounds related to entropy sort of required that. We don't want to talk about second order or third order entropy. So we talked about what if we assumed that every character of our sequence was sampled from the same distribution independently. But these are not generally realistic assumptions. If they were, it would be great. If we could do something to guarantee that our sequence, by the time it reaches an entropy coder, is a bunch of independent things, that would make our lives a lot easier. But one thing we've seen so far in this course is that unfortunately our lives are just intractably difficult a lot of the time. So really, we could change the distribution. I could decide that after the first character, we're going to change this distribution and, for example, use one where C is far more common than B. So notice how in our first character, B was relatively more common than certainly C or D. It wasn't the most common, A was the most common. And yet I've decided when I zoom in on B, maybe the distribution changes. For example, maybe I can leverage information I know about what characters in my input sequence, which may not be full of independently occurring symbols, what characters in my input sequence are most likely to follow B. And maybe it's the case that C and D are very likely to occur after B, whereas A and B aren't. And there are a variety of reasons I might want to do this. So I could even go further. I could adjust the distribution at every single step. After I've seen a BC, I might realize that A is very common after BC, whereas B isn't and C isn't, but D, I don't know, sort of is. So there are reasons you might want to do this, and we have to keep in mind that by doing this, we are sort of departing from our view of arithmetic coding as a strict entropy coding technique. It is still performing entropy coding, but we're tweaking the distribution at each step based on other knowledge that doesn't really fit into our model of information from earlier in the course. But that's fine. Our goal is to save bits. Our goal isn't necessarily to maintain some level of theoretical purity of what we view information content or entropy as. So let's think about reasons we might want to do that. I'm going to use the term adaptive encoding to refer to one specific thing, which is where the distribution evolves over the course of the algorithm. But in practice, the word adaptive is applied to a lot of different methods where the probabilities of each symbol might vary. So as I progress through the sequence, the probability that I encode each symbol with might change. So if I have a sequence like this, obviously our overarching goal, so we don't care that much. If I'm trying to save bits, I don't care that much about entropy bounds or information content. What I care about is using a method that generates the fewest bits. That's it. We need to know about information and entropy to derive these methods and understand them. But in practice, I'm willing to sacrifice some of that theoretical stuff in the service of saving bits. Really, in arithmetic coding terms, what I want at every step is for the coder, when it's processing each character, to encode that character with as large a probability as possible. That's it. Because we know that if I'm able to encode A with a probability of, I don't know, 90% or something, then I'm going to use fewer bits. We saw over the last couple of lectures that the larger the probability window for the symbol, the fewer bits that you need. If I can engineer some clever way for the encoder to encode every symbol as it goes through my sequence with a very high probability, I'm going to save bits. If that means tweaking the distribution at each step in such a way that the decoder still knows what I'm up to, then so be it. So there are a couple of ways I want to approach this. There are a couple of reasons why this adaptive idea, changing my distribution at each step, can be helpful. One of them is actually related to overhead. The other one is related to leveraging context, and I think that's the one I've already telegraphed a bit, so we'll talk about that one first. For the sake of being able to visualize this a little bit, what I have done is I have taken the complete text of A Tale of Two Cities, a book we just keep hearing about, but yet probably none of us have actually read yet, and I have looked only at the uppercase and lowercase letters. So A Tale of Two Cities is a large piece of English text. It does have spaces and punctuation and some formatting characters for things like chapter headings, but for the most part, the vast majority of it is English text, so a bunch of uppercase and lowercase letters that form English words. We understand, therefore, that an English word is not a sequence of independent symbols sampled independently from the same distribution, obviously, because English text contains patterns. But if we look at it only as that, so if I just look at the probability of each character in a vacuum, I get this table here. I have ranked the table in descending order, so E is the lowercase e is the most frequently occurring character. For the sake of computing this, just to make the visualization easier, when I generated this data, I completely ignored all characters that were not letters. Now, so I'm declaring that here. I don't think it affects the viability of the point that I'm going to make. So that means that actually E occurs a bit less frequently than 12% in an absolute sense because there are also spaces and punctuation to account for. I just want to talk about the part of the text consisting of English words. So among all the English words, E occurs 12% of the time, lowercase e. Uppercase E actually occurs less than some other uppercase letters because probably I only see uppercase letters in a book like this at the beginning of sentences or for proper nouns. And there aren't very many words that begin with uppercase E, I guess, whereas E occurs pretty frequently in English text otherwise. So we'll notice that the most frequently occurring characters, just like English as a whole, are E, T, A, O, and then I is a little bit less frequently occurring than in English as a whole, but these are pretty unsurprising in English for common characters. And then things like S and H and D and R and L and U, which are also very common English characters, also show up pretty high in the ranking. Okay, great. So we could employ arithmetic coding on the set of probabilities from this book, if we bring back the non-alphabetical characters, and achieve some benefit, because E certainly occurs far more often than it would if we assumed characters were distributed uniformly. But that's not the point I want to make. The point I want to make is that in English text, if I take advantage of context, if I'm looking at the character right after a Q or the character right after a T, I might notice that probabilities change a bit. So T itself is pretty common. But notice how E is much more common than T. And if I use the global table for everything, then I suppose I have to assume that the most frequently occurring character after a T, under the assumption of independence, is an E. We may understand in English, certainly TE occurs a decent number of times in English words, but also in English we tend to see THs a lot. So we could actually analyze this book in terms of not just the occurrence of individual characters in a vacuum, but the probability of seeing a particular character after some other character. So for example, let's look at T. If the previous character was lowercase t, what is the probability? What are the probability distribution of the next character that could occur? And we notice that actually after a lowercase t, H occurs with about 45% probability. And E, which was the most common character in general, is now ranked third. It goes from 12% down to 10%, or down to about 11%. Whereas H is now 45%. And that's a really big deal, because if I'm running arithmetic coding and I'm able to ascertain that in advance, if both encoder and decoder can be informed that characters after T are much more likely to be H than anything else, so with 44%, then H can get encoded with a probability of 44 or 45%. And we know that obviously 45% is a great deal larger than 6%, and that means that I'm going to save a lot of bits by leveraging context. There's still the question of how exactly does the decoder know what I'm doing? Because I assume if I'm doing general compression, that the decoder doesn't know I'm working with English text. All it can learn is what I tell it explicitly, or maybe what it can pick up on from previous characters that it's read and worked with. But that's one really strong argument for being able to manipulate my probability table at each step, leveraging context, leveraging knowledge of previous characters, like the character right before, or maybe a multi-character sequence right before the current character. If I take a look at Q, it's almost ridiculous. So inside A Tale of Two Cities, there is literally nothing that occurs after a lowercase q besides a U. U actually appears with probability 1.0. These dashes mean that the character doesn't appear at all. Just for a sense of contrast, this uppercase Q here occurs with some non-zero probability, just a very small one, but uppercase Z literally never occurs. For whatever reason, in A Tale of Two Cities, Charles Dickens never needs an uppercase Z. And so in A Tale of Two Cities, after the lowercase letter Q, all you're ever going to see is the lowercase letter U, with probability 1.0. And I think we can agree that probability 1.0 is a much larger number than the global probability of U, which is 2.7%. So I'm going to go out on a limb there here and say that 2.7 or 2.8% is significantly smaller than 100%. So one other disclaimer I have to give before we go any further. So I'm going to differentiate between context-based and adaptive schemes. As I said, many sources just call all of these things adaptive. It's a question of what's adapting. For the sake of this lecture, I think some differentiation is sort of helpful. These techniques are not specific to arithmetic coding. I'm using arithmetic coding as a vehicle for this because it's really easy to manipulate probability tables. However, any entropy coding scheme or any scheme that relies on probabilities can be adjusted so that you modify the probabilities at every step. So both encoder and decoder modify their view of probabilities as the algorithm progresses. The difference is if you were to write adaptive Huffman coding, which does exist and is a very powerful algorithm, it requires quite a bit more work, and it's a bit harder to visualize what it's really doing. And it's that latter point that really motivates my presentation in terms of arithmetic coding, because we're used to this type of diagram for arithmetic coding, and the Huffman coding version of this diagram is a bit harder to sort of visualize. I'm not going to talk about adaptive Huffman coding, but it is a thing, and it is a very valid thing. So don't assume from my omitting it that somehow adaptive Huffman coding isn't useful. It is quite useful, it's just that it's a little bit harder to visualize. The goal of this lecture is talking about the adaptive part, not necessarily the arithmetic coding part. So we're going to focus on arithmetic coding. In the rest of this lecture, I'm going to talk about these adaptive methods as if I'm plugging the resulting probabilities, these modified probabilities that I'm changing at each step, as if I'm plugging them into an arithmetic coding technique. But really, I could plug them into any entropy coding technique. There's also this other point that we haven't gotten to yet regarding arithmetic coding that we really have to cover, which is in all of the examples where I showed off how great arithmetic coding was, we have assumed that both encoder and decoder started with this probability table. That is, when the encoder began encoding, it had access to the probability distribution of all of the input symbols. And that's one thing, because of course, if we read a block of data, the encoder could figure that out. But we also assumed that the decompressor had that the arithmetic decoder had access to the complete probability table. Because if it didn't, how is it going to perform decoding? We just assumed that that was possible, and I made a couple of offhand remarks like, well, yeah, the encoder has to send this to the decoder. So just like in Huffman coding, where we have to send over the code that we use, so in prefix coding we can send over a tree, we can send over a table of code lengths, whatever, we have to, in the form of overhead, provide the decompressor with knowledge about the code that we're using. Just like in that case, arithmetic coding has some overhead in the model we've already presented that is necessary, which is we have to give the decompressor our probability table. My claim over the next couple of slides is that that's a little bit higher maintenance with arithmetic coding because of the real number aspect of it than it is with Huffman coding, where I can send a table of code lengths. So if I want to send the decompressor the complete probability table, I mean, if we put aside for the moment the fact that this means I have to derive the probabilities before I do encoding, which is annoying because it sort of runs the risk of breaking our streaming requirement. If I ignore that, if I want to send the decompressor my probability table, what are my options? Okay, well, I guess I can either send it as literal real-valued probabilities or as a table of frequencies. So numerator and denominator, basically. I send over the numerators, the frequencies, and then you can produce whatever probability data you want on the fly, like we did in the last lecture. So if I send over real-valued probabilities, that's sort of nasty. I don't actually have to use a floating point type. I have to use a real-valued type. I could use a fixed point type because all of my probabilities are between 0 and 1. I say floating point in the sort of colloquial sense of I need to send real numbers. The problem with that is that I have to make sure that no rounding errors occur in transit that I don't know. So if I'm the encoder, I have to make sure that the decoder is using literally bit-for-bit identical probabilities to what I'm using. So any rounding that's performed in transit, I have to make sure I catch up with myself on the encoder side, so there's no errors between encoder and decoder. So that's one problem. There's also the problem that if I have a bunch of real numbers, so floating point or fixed point values that are approximating infinite precision real values, then how am I going to send that table of probabilities? We've seen with code length tables in prefix coding, I could use delta compression or RLE. But how is that going to work? I mean, how likely is it that I have a bunch of symbols that have literally exactly the same probability value? I mean, that's possible, but is it that likely? Many of the benefits of arithmetic coding seem associated with there being a lot of distinct probabilities. So how likely is it I'm going to have a bunch of probabilities in a row that are the same? Well, not very likely. So RLE is not really going to help us very much. What about delta compression? Okay, well, if I use delta compression and I've got two probabilities next to each other that are similar, then I could encode those as a delta value, so plus 0.002. But now I need a way of encoding delta values that are real numbers that have some decimal expansion, not just, plus 1, plus 2. I actually have to do plus 0.002. And also there's the problem that if I look at my different symbols, so there's A and there's B. In general, there shouldn't, I don't really expect there to be much of a correlation between the probability values of two symbols because I'm just encoding symbols in some random order. So for example, if I look at all 8-bit symbols, I have no idea what the significance of those 8-bit values is in the context of my input. So it could be that A has probability 0.163 and B has probability, 0.361. There's no reason why they need to have probabilities or even cumulative probabilities that are that close together. And so delta compression doesn't really help me much there. Now, to be sure, in prefix coding, obviously, this also is the case. I mean, in prefix coding, I don't expect that the code length for A has much of a relationship with the code length for B. The difference is that in prefix coding, I will normally impose some length restriction on the length of my prefix code. So I'll say every prefix code has length at most 15, like deflate, or 20, like bzip. And that means that if I use delta compression, at worst, I'm encoding deltas of, like plus 19, or plus 20, or minus 20, as opposed to encoding deltas of some weird arbitrary value like like 258 or some weird thing like that. So I can't leverage delta compression or RLE in the same way I could with prefix coding. What about tables of frequencies? Okay, well, same problem, right? Ultimately, I can encode the frequency table using integer values, but my numerators, my frequencies could be huge numbers. If I want a frequency table with large granularity, I'll want to encode large frequency values. I won't want to divide them by some mutual divisor or something to simplify them like I would at the end of the last lecture, unless I really have to, unless I'm running out of precision. And so I can't really employ delta compression or RLE on those either. So frequencies or probabilities, and I should say if you're going to do this, you should just send the frequency table. Don't try and send it as real valued probabilities. That's going to be a problem for lossless compression. So if I send a frequency table, I don't really have the same set of tricks that I can use to compress that frequency table as I would with a code length table with prefix coding. And it turns out actually that the techniques we're about to see, these adaptive techniques, are often used in practice. So instead of sending tables. So that is, although we've been covering arithmetic coding using the true probability table, in practice often arithmetic coders don't do that. They use an adaptive scheme as a way of avoiding having to send over the table in advance. Because as we'll see shortly, in adaptive schemes, you can send no overhead at all. You can have the probability distribution be learned on the fly by the decompressor, which is nice when you don't otherwise have a way of sending over that table. And it's an interesting contrast to prefix coding and Huffman coding, where we have developed some techniques for sending over tables that work, I don't know, well enough. And so actually it turns out that we can apply some of these logistical concerns to Huffman trees, although, as I've just said, we have ways of encoding code length tables. So we have a way around that problem. It's not ideal. Obviously, the code length tables do take up space, but the properties of code length tables, and the amount of work that's gone into encoding them in the past does give us an option there. Now, there's also this point that I've said a couple of times, which is if I want to send over a probability table, or frankly, a code length table, I have to look at my input in advance and compute its probability distribution, which means it sort of forces me to divide the input into blocks if I want to do something approaching streaming compression. So here's an idea. Why don't we just not send over the probability distribution? How about we both, so I'll be the compressor, you be the decompressor. How about both of us start with no knowledge whatsoever of the actual distribution of symbols? And what we'll do is start by assuming that every symbol occurs with exactly the same probability. So 0.25, 0.25, 0.25, 0.25. Or if you like, if we'd rather use frequencies, let's assume that everything occurs already with frequency 1. And that means that each probability is now implicitly 1 over 4. So I'm going to start by assuming every symbol occurs equally often. And then, as I go through the input, at each step, I'm going to modify my frequency table. And the decompressor can do the same. The decompressor will start from the same basic distribution and make the same modifications at each step. We know from the previous 2 lectures that in arithmetic coding, the decompressor can stay 1 step ahead of me. It can always figure out one more symbol if it knows the distribution that I worked with at the beginning of the previous step, which is going to be the case here. So what will happen is I start by assuming every symbol has the same frequency, and then if I see, let's say I see 2 A's, then a B, then a C, then an A. As I see each symbol, I'll say, well, hey, I just saw an A. I guess that means A's are more frequent than I thought. So I'll add 1 to the frequency of A. So now implicitly the probability of A is 2 over 5 instead of 1 over 4. Oh, there's another A. Okay, so I just encoded the second A. I will now modify this to be 3. So now it's 3 over 6, or in fact by now 1/2. And so because A's have been observed to be common, if I see any more A's, I'll encode them with a high probability. And it's understood in all of this, the cumulative frequencies are going to be adjusted in the background too. Whenever I modify the frequency of a symbol, I have to go modify my cumulative frequency table, which takes time, but it doesn't take bandwidth. I can do that using processor time, but without having to send anything through the bit stream, as long as both me and the decompressor agree to abide by the same protocol. So the idea is I'm going to start with no knowledge of my distribution, and I'm going to develop my distribution over time as I see each symbol. Let's just do one more. So I see that first B, I'll say, oh, I'll increment the frequency of B accordingly. And notice that as I go, symbols I've seen a lot before will have higher frequencies and therefore be encoded more efficiently than symbols I haven't seen before, which is sort of nice, because if I haven't already seen a C or a D, maybe it's a bit less likely that I'm going to see too many C's or D's in my sequence. So basically I assume every character to begin with the same probability, and then each time I see a particular symbol, let's call it SI, that probability increases for future iterations. So specifically, what I sort of want is actually this. I sort of want the probability at each step of a particular symbol to be the number of symbols of that type I've seen so far over the total number of symbols I have processed. I can't quite do that because if I've never seen SI before, that means that the probability of SI is going to be 0 over something, which means its probability is, of course, just 0. And what if the next symbol is SI? Well, I can't encode it if it has a probability of 0. That's impossible. I need there to be some interval for me to encode it into with arithmetic coding. So I'm not allowed to have a probability of 0. So to accommodate that a little bit, what I can do is, I don't know, give each symbol a little bit of a bonus. And this is basically equivalent to my idea from a minute ago where I start every symbol off as if I've already seen it once. That's really what's happening here. The probability of each symbol is now the number of instances of that symbol plus 1. That one bonus I give it at the beginning, divided by the number of symbols I've processed plus k, k being the number of symbols. In other words, the sum of all of the bonuses that I gave out. Every symbol gets a bonus of 1, and there are k symbols, so the total number of bonuses is k. Now, this term actually does sort of throw off the ultimate distribution, and I'll come back to this in a few minutes, but it does ensure that at every single step, every single symbol always has a non-zero probability. And I should observe that as these numbers get larger and larger, so the number of instances of a particular symbol and the number of symbols processed, the contribution of this part to the ultimate probability decreases. It slowly goes towards 0. So although it does throw us off a little bit from the true distribution over time, it does provide us an exit strategy just in case we need to encode a symbol we haven't seen yet. That's not the only exit strategy, though. I'll talk about another exit strategy in a few minutes. So this is an example of this is something called statistical modeling. It's one of many examples, and because statistical modeling has become so important in computer science, many of you are already familiar with various modeling techniques. This is a very simple modeling approach, so I'm trying to predict the probability of future symbols using information that I've gathered from somewhere. In this case, I've gathered it from previous symbols entirely. So I'm modeling what I expect to see based on what I've already seen. Usually when we use these adaptive encoding schemes, they're a combination of some probability-based encoding strategy, so entropy coder like arithmetic coding or Huffman coding, and some modeling strategy where the model changes over time. And the idea behind this is the actual modeling itself doesn't happen inside of the bit stream. The compressor and decompressor can compute these probabilities at each step with just processor time and memory, as opposed to bits in the bit stream. And I'll illustrate that as we go forward. Let's just do a full encoding with this scheme. I'm not going to bother with an end of sequence marker, but we know that we could add one if we wanted to. So if we want to encode this sequence here, which I'm going to encode a few times in this lecture, we start with a uniform distribution. So everything gets a frequency of 1, which guarantees that everything has a non-zero probability. And then I'm going to walk through and I'm going to encode each symbol. And after I've encoded each symbol, I'm going to update the frequency entry in the symbol in the table of frequencies. In the visualization, just to be clear, this table, when it gets updated, the update that I show will be the update that took effect after the encoding of the current character. So if this character A turns red, that means it's the character I'm currently encoding. The table reflects what I have after encoding that character. The reason that's important is it makes sure the decompressor can stay synchronized. As long as the decompressor knows that my next character is the letter A, which we know from previous lectures, it can figure that out, the decompressor can then perform the same update at the end of the step that I am performing in the compression. All right, so after encoding A, the frequency of A goes up a little bit. The range that I get after encoding A, though, so low and high, is based on the old table, based on the table before this step. Okay, so I update the frequency of A. That, of course, updates the probability of A, and it requires me to shift the cumulative frequencies. So going back a bit, I'll just clean up this mess. Notice how the low bound of the range for D was previously 0.166, repeating, or 167 if we round. Now it's 0.286, because I've just given A more real estate. So performing this increment requires me to recompute some amount of the cumulative frequency or probability table. Not necessarily all of it, but maybe all of it. In the worst case, I do have to recompute all of the entries. The amount that I have to recompute just depends on where the symbol I'm incrementing lies in the interval. So I have to recompute it, but that recomputation just takes time. I don't have to encode any extra bits to do the recomputation. The decompressor makes the same update that I make, and the decompressor performs the same recomputation that I perform. So I'm using more processor time, but I'm still not using any more bits. And ideally, in exchange, I'm saving some bits by developing a more accurate picture of probabilities as I go. So I update the probability for A there. So now A has a larger window, which is nice if I see more A's. And so then I encode the space and I increment the probability for the space character there. There it is. And then I encode the S, okay, and I keep going. Then I encode another A. And of course now when I encode this second A, I benefit from the larger window that I had for A here. Okay, and so then I keep encoding. There's the D, there's the space. And as I go, notice that this frequency table is slowly approaching, in a certain sense, not completely, as I'll come back to in a minute, but the frequency table is slowly learning the true frequencies of each character. The probabilities that I'm getting are slowly approaching the true probability distribution of the sequence. And were this sequence to go on for a long time, as time went by, this table would be more and more accurate to the true distribution, even though neither compressor nor decompressor have actually computed the true distribution at any time. Okay, so I'll keep walking, and we get to the end here. And for the sake of comparison in a minute, I could choose this 14-digit, if I use base 10, representative. If I were to use arithmetic coding from the true distribution, that would be this. So if I were to start from scratch using an arithmetic coder like the one I used in the previous two lectures, I could compute a 12-digit representative instead of a 14-digit representative. On the other hand, if I wanted to use the true distribution, I would have to send this entire table in some form to the decompressor in advance. And I'll bet that those extra 2 digits that you save take up way less space than sending this entire table. So maybe it's easier to just work with the 14-digit version and not send the table and have the distribution get learned by the decompressor and the compressor as they go. Also observe, here is the true distribution, so 6, 1, 2, 4, 3, 1, and notice that the distribution in my adaptive table is 7, 2, 3, 5, 4, 2. And that actually is just the same frequencies but plus 1. So of course, once I've gotten to the end of my sequence, I have all the same frequency data that's in the true probability table, except I've added 1 to all of them because I gave every symbol a bonus of 1 at the beginning. But that extra 1 is going to mean less and less as time goes by, because as my total frequency increases, as the frequency of A goes up further and further, once it gets to 600 and D gets to 1 or whatever, as I have these larger and larger values, that off by 1 is going to mean less and less to me. So what I've been able to do is basically learn the distribution over time. And maybe you can also observe that if I look at the true probability, or the learned probability of A is 0.304 at the end, the true probability is actually a bit higher than that. It's 0.353. But the learned probability is 0.304 at the end. But if I scroll back a bit, notice how earlier on, the probability of A is still pretty close to 0.3. So actually, I have a pretty good approximation of my real distribution without actually encoding the entire sequence. And if a sequence gets longer and longer, I can expect, and this is also by sort of basic principles of probability and statistics that you probably know from some earlier course, that if I'm encoding a sequence of 4,000 things, and I encode the first 1,000 things, on average, unless there's some overarching pattern that makes the distribution lopsided, on average, I can expect, after encoding some subset of my data, to have a pretty good approximation of its true distribution from my observations. This idea of learning the distribution can actually pay off in a lot of different ways. It gives me a pretty good approximation pretty quickly, and I really I get to work around that annoying problem of sending over my probability table. Just for proof that the decompressor can actually do something with this, I have some slides. I'm just going to skim over them quickly. I have some slides showing the decompression process. So if I start from that 14-digit representative I chose here, and I start decoding. After one decoding step, the decompressor was able to figure out that it was an A. Here's my value V. And so it increments the frequency of A. The decompressor starts off with the all ones frequency table, a uniform distribution. But after one step, it increments the frequency of A. And as you can see, it is now caught up to the end of the first step of compression. It'll be able to duplicate the first step of compression and keep walking through it, and at each step make the same set of updates. And so, of course, it can stay caught up, and therefore we do not have to tell the decompressor anything besides, of course, making sure the decompressor is programmed to know this trick, to know that we're using an adaptive model. We don't have to tell the decompressor anything in advance about the distribution of symbols. It learns the distribution just like we do in the compression step. All right, and there we go. So when we talked about using this true distribution, that was a way of interpreting the arithmetic coder as an entropy coding technique that allows us to achieve entropy. So just like how we talked about how, the number of bits Huffman coding might use and compared that number to entropy via the computation of L bar versus entropy, we understood that if we use a Huffman coder and we achieve a certain L bar, that L bar doesn't encapsulate the overhead of sending over the code, so sending the code length table or the tree or whatever. Similarly, if we talk about the efficiency of arithmetic coding in an abstract sense using the true distribution, that isn't taking into account the number of bits we have to use to encode the probability table. But I should observe that if we do use the true distribution and think about the average number of bits per symbol that arithmetic coding uses, it does actually approach entropy. So as the sequence gets larger and larger, the input sequence, the number of bits produced by arithmetic coding will converge towards the lower bound given by entropy for a sequence of independent symbols and whatever. But we've now seen that actually in practice, maybe we don't want to do that. Maybe we're willing to sacrifice a few bits here and there and not achieve entropy in the theoretical sense in exchange for saving on some overhead, because overhead is a very serious practical concern. So that adaptive model I just showed off, the very simple one that starts with a uniform distribution and learns the distribution, that isn't competitive with the true distribution in terms of the representative length. So we had 14 digits versus 12. But on the other hand, I don't care about distinctions like this. I care about saving bits overall. So notice how I didn't need to send literally any metadata. There was no overhead. Compressor and decompressor all they were sharing were the bits of the representative, was that bit sequence. There was no need for the compressor to send the decompressor literally anything else. Anything else that the decompressor needed to know, it could learn as it went. And so although it's true that yes, if we had the true distribution on hand, arithmetic coding could get us to entropy, we care about bits. We don't care that much about entropy. We need to know about entropy, but we don't care that much about entropy in the practical sense. We care about using as few bits as possible. And so this adaptive model is very attractive for that reason. Sending the probability table is sort of a mess, whereas learning the probability table doesn't seem to cost us that much, and it saves a whole ton of overhead. Now, we could, of course, I keep saying this, we could apply the same adaptive trick to a prefix coding scheme and then not send a code length table. So this is not an inherent advantage of arithmetic coding. It's an advantage of this adaptive idea. However, the disadvantage, I guess, of sending a code length table is a bit less severe than the disadvantage of sending the probability table, and that's one reason why encoding the code length table is often something we can just put up with, because we have ways of sending over code length tables. But this is still a viable option if you'd rather not send a code length table with a prefix code. Now, there are certain forms of overhead that actually can help us. I mean, sending a code length table is a form of overhead that can help us because we have the code established and we can then just use it. And if the code is efficient, we don't have to sacrifice the same number of bits that we would do in an adaptive encoding. And especially if we have some very efficient way of encoding a code length table, maybe it's no big deal. Introducing certain forms of overhead can be helpful, whether it be sending a table of stuff in advance or not. There are ways we could fold overhead into our bit stream as we create it, as a way of basically having an out-of-band communication between compressor and decompressor. I'm going to draw one of these diagrams. It's been a while since I've drawn this. So we've got our usual bit stream between compressor and decompressor. And we just saw that with this adaptive arithmetic encoding model, we could just send the representative bits. Wouldn't it be great, though, if, since the decompressor can now modify its table at each step, if there are times when the compressor wants to send the decompressor a little hint, maybe change your table, maybe do this, maybe make this other decision which will increase efficiency going forward, wouldn't it be great if there were a way for the compressor to send the decompressor hints, sort of out-of-band information? Not the representative bits, really, not actually the input sequence, but some other bits telling the decompressor about maybe to switch modes or something similar. So we'll see that there actually are ways of doing that. We can actually, what we do is we just make up extra symbols, and these symbols have a special meaning that isn't about the input sequence, but is instead about decisions the compressor wants to make. We use those to send out-of-band information. We can also, without sending extra information, do things like weight the probabilities that we use at each step based on predictions. We could bring in a predictive modeling approach. We could use previous characters as a way of making those predictions. So I could say, hey, you just send me the letter Q. Maybe I'm going to change my model of probabilities based on what I've previously seen after the letter Q, because I know that certainly in data that might contain patterns like this, the differences in probability contingent on the previous character can be massive. So one example of how I might do that is, suppose we think of a three-symbol model again. So I've got just three symbols, A, B, and C. If I want to leverage the characteristics, the sort of unique characteristics of symbols following A's, or symbols following B's, or symbols following C's, what I could do is I could maintain three separate probability tables. One probability table that I use only for the symbols that occur after A's, one probability table that I use only for the symbols that occur after B's, and one that I use only for symbols that occur after C's. And I could use the same adaptive approach. Every time I see an A followed by an A, then I'll increment this number. When I see a B followed by an A, I'll increment this number. So that next time I go to encode a letter that comes after a B, I will have maybe a more nuanced picture of the probabilities of symbols that come after B. And then at each step, the decompressor and compressor, both of them are going to be maintaining all three tables from the beginning. At each step, they each just update whichever table applies. So no extra information needs to be sent. It's the same as the earlier adaptive model, just more specialized. And so we start with a uniform distribution for each table because we know nothing about the characteristics of our input data. And hopefully you can agree that you could generalize this from 3 characters to 256 with minimal extra work. It would just require a lot of extra memory, but not bitstream bits. It would just require bits in memory on the machine running the compressor and the machine running the decompressor. No extra bits would need to be sent. And then over time, we would develop things like this. So maybe I notice that in this particular input, if I look at the character that comes after an A, it's way more likely to be a B than anything else. If I look at the character that comes after a C, it's way more likely to be a C than anything else. And this is great because if I go to encode a character that comes after a C, then I will encode it with this probability table, which weights C's much higher. So therefore, if I encode a C, I end up encoding it in an absolutely tiny number. So this is less than 1 bit. This is a tiny number of bits, which is a pretty big deal. And so, of course, I could generalize this not just to 256 possible symbols, but also not just to one previous character. I could have, up to the limits of my computer's memory, I could begin talking about what is the probability table for characters that come after 2 A's in a row. And the more of this data I maintain, such that the decompressor can also maintain the same data, the more nuanced my probabilities are going to be, and the better off I'm going to be if the patterns that I've noticed in previous characters persist in future ones. So if in general, in the next few thousand symbols I see, the character after A is still likely to be a B, I'll be encoding those B's with an extremely high probability and therefore in very few bits, which of course will save me quite a bit over a generic arithmetic coding model that assumes all symbols are independent. So of course this requires lots of memory and processing time, but to be honest, we've got lots of memory and processing time. We just want to save bits. Now, let's go back to that model from earlier. Let's talk about this idea of having the compressor and decompressor send hints. So I want the compressor to be able to send the decompressor out-of-band information to give it a hint as a way of saving a few bits. So that earlier model that we used, the basic adaptive model, started by giving every symbol a frequency of 1. It gives every symbol a frequency of 1, a sort of bonus to make sure that it always has a non-zero probability. That can be a little bit wasteful. So I mean, the most obvious example is, what if D never occurs? If D never occurs, then as time goes by, all of these numbers get incremented. So that's going to be, let's make that 17, this is 187, and this is 10, or whatever. As time goes by, this never gets used, so its frequency stays at 1. And that does mean that over time, its probability gets smaller and smaller, because the other frequencies go up, which narrows the window for D. But D is still taking up space. It's still eating up a little bit of my probability window, and that's still going to put a drag on my efficiency. If only one symbol has that problem, maybe that's not the end of the world. What if we have a huge number of symbols? So I've got X, I've got Y, I've got Z. All of them get a bonus of frequency 1. What if, let's say, none of these 5 symbols ever occurs? They need to begin with a frequency of 1 because in this model, I have to have some way of encoding them if they do occur. And in this model, the only way of doing that is to give them a frequency of 1. If all of these have a frequency of 1 and none of them occur, they're going to eat up a pretty sizable chunk of real estate at each step. It'll go down over time, but it's still a pretty decent amount of real estate. And that's a problem. That's going to eat away at my efficiency. What would be sort of nice is to have maybe a single symbol that I use to indicate to the decompressor, hey, you're about to see a symbol you haven't seen before, as opposed to giving every symbol a free frequency of 1 so that I can always use it. So I have to ensure that every symbol that could possibly appear has a non-zero probability because it's impossible to encode symbols that have probabilities of 0. But I don't necessarily have to do it this way. I have other tricks I could try. So I don't want to waste more probability window than I have to. I might have to waste a little bit. There will be a little bit of inefficiency resulting from my adaptive model, but I'd like to reduce it. So here's an idea. I'm going to maintain 2 different tables. I'm going to maintain one table that is always a uniform distribution, and one table that is my adaptive table from earlier that I will learn over time. But notice here, in this example, the adaptive distribution starts at 0. So not at 1. So no symbol gets free space here. The adaptive distribution starts at 0. By default, the compressor and decompressor for every single symbol will default to this table here. But you can see there are going to be cases where this table isn't going to work. For example, right at the beginning, if I want to encode that first A, how am I going to do it? It has a probability of 0. So why not have it so that the table begins with frequencies of 0? If you get stuck, if you can't encode using this table, you're allowed to send the decompressor a hint that tells it, okay, for this one step, please switch over to the uniform table. And we have to have a way of doing that. We have to have something we can send the decompressor that does that. But remember that I've just said at every step, both compressor and decompressor start in this table here. That means if I'm going to send the decompressor a symbol, it has to be a symbol from this table here, which does put me in a bit of a tight spot. So what I'm going to do is I'm going to make up a brand new symbol. I'm going to call this an escape symbol. So it's a symbol that doesn't exist in the input and isn't really about the input. It's a way of sending hints to my decompressor. I'm going to have one escape symbol, but really we could make up 1,000 escape symbols. In this lecture, I only ever use one of them, but you could make up 10 of them. Think about the escape symbol similar to like the end of message marker or the values RA or RB in BZIP. They're special symbols I've made up for operational reasons, for logistical purposes. You could even think about the length symbols from deflate as being a certain type of escape symbol. So escape symbols are symbols I make up for the sake of the compressor sending the decompressor a special coded message. I'm going to denote the escape symbol by this thing, because I feel like the escape symbol is sort of cool and mysterious, and also because at least once a semester I've got to drag out my table of LaTeX codes for interesting mathematical symbols, and so this was the lecture where I did that. So this is going to be my escape symbol, this strange looking symbol here. And the idea is the escape symbol will always have a frequency of 1 in my adaptive distribution. And if the decompressor, which for every symbol the decompressor will start by looking at the adaptive distribution, and it will expect me to send it a symbol from the adaptive distribution. If I were to send it the escape symbol, the decompressor will interpret that as, oh, that's not a real part of my input. Instead, that's telling the decompressor, switch over to the uniform table, and then you'll get a symbol I've sent you from that. In the uniform table, the escape symbol has a probability of 0. In this context, the reason for that is that when I send the escape symbol, I'm telling the decompressor, for one symbol only, switch over to this table, and then for the next symbol, switch back to the adaptive distribution. So So there should be no reason for me to send the escape symbol in the uniform distribution, because if I send the escape symbol in the adaptive distribution, I'm telling the decompressor to go over to the uniform table. There's no reason I'd want it to switch back at the same step. All right, so to encode the character A, so if I'm sitting on this table here, if I want to encode the character A, I can't. It's not available in the adaptive distribution. It has a probability of 0, so I can't do it. So I tell the decompressor, switch over to the uniform distribution. I send over the escape symbol. Now, I'm sending it with a probability of 1.0, which is allowed, but is sort of weird. And I'll come back to what it means to encode something with probability 1.0 later. It turns out it's actually pretty good news. So I send the escape symbol, and then I go over to the uniform table and I encode the symbol A, which means I'm sending over, the next thing I'm sending is the symbol A with probability 0.2. So the decompressor actually now gets 2 symbols as part of me encoding A. One symbol to tell it to use the uniform table, one symbol which is actually encoded using the uniform table, which is the character A. Once I've done that, both compressor and decompressor increment the frequency of A in the adaptive distribution. So the next time I encode an A, I can encode it here. And notice that if I were to see another A right now, it would be encoded with probability 0.5, which is pretty good. That's a big value, which means I'm saving bits. Okay, so again, in this scheme, whenever I tell the decompressor to switch tables, that switch only applies for one symbol. So at the beginning of the next symbol, so once it's seen a real symbol, so anything other than the escape symbol, once it's seen a real symbol, the decompressor and compressor will both automatically switch back to this table here. That means once I encode the space, when I want to encode that space character, I'm trying to encode it from this table. So I have to again encode an escape symbol, and then I have to encode the space from the uniform distribution. And to do that, the escape symbol now gets encoded with probability 0.5. And so I encoded this with 0.5, and the space gets encoded with 0.2. Which means that obviously I'm using a bit of bandwidth for both of those symbols in this case, and that's just a compromise I have to make. In exchange, notice that the adaptive distribution doesn't get polluted with all those free ones that I was granting earlier. I only have a free one in the case of the escape symbol. All right, so I send over the first S. I send my second A. When I send my second A, it'll be after this step here, which means I get to send the second A with probability 0.25. As opposed to what it would be if I had a bunch of ones in these positions. Once I'm done sending the second A, I increment its frequency. If I send a third A now, it would be encoded with probability 0.4. Okay, so I keep walking. In cases where I need a symbol that isn't available, I have to go backwards into the uniform distribution using the escape symbol. But over time, notice that the probability of my escape symbol goes down, as I expect it to, because the other probabilities fill out the table. But also, I should expect that I'll use my escape symbol less, because I only need the escape symbol the first time I see a particular thing. So the first time I saw a D or an S or a space or an A. And that means as time goes by, it's less likely that I'll need the escape symbol, so the fact that its probability goes down sort of makes sense. There's the L, and actually at this step, I'm done with the escape symbol. As far as as far as I can tell, I will never need the escape symbol again. A more crafty adaptive approach might even set the frequency of the escape symbol back to 0 at this point, because both compressor and decompressor can verify they will never need the escape symbol again. And by doing this, we're not going to do this, but if we were to set this frequency back to 0, we'd save a bit more bandwidth. We would increase efficiency. All right, so I finish encoding. Notice how in this example, I'm not even bothering to show the low and high values. We know that we could generate those. I'm just showing the model, because as time goes by, I'm going to run out of space on my slides otherwise. I just answered this, so I talked ahead of the slides a bit. We observed that when I used most symbols, like A, I would increment their frequency. And yet I never incremented the frequency of the escape symbol. And that's because unlike A or D or L or any of the other real symbols, where I want their frequencies to increase as I see them so that my observed probability distribution becomes more accurate, the escape symbol becomes less useful over time. And therefore it makes sense not to increment its frequency, because every time I see it, I'm less likely to see it in the future. We like it if its probability value sort of goes down naturally over time. But then there's this again. So I mentioned at the beginning that first thing we sent, when I was encoding the A, I sent over escape symbol and then A. And this is the table before the increment, and observe that means I sent the escape symbol with probability 1. Is that allowed? I mean, we saw earlier, we're certainly not allowed to encode things with probability 0. are we allowed to encode things with probability 1? Well, obviously the answer is yes, because, I did that. But it feels a little bit creepy that we're allowed to do that. So what I've really done there is my low was 0 and my high was 1. I then encoded something with probability 1, which means the cumulative probability for this was 0, and the 0 through 1, so that was the interval. I guess we'll draw it like this as a half-open interval, which means that when I was done zooming, I just zoomed back in on 0 and 1. In other words, my interval didn't change size. And if you think about that carefully, you'll realize that in the arithmetic coding algorithm, if the interval didn't change size, if low and high didn't change, there's no way I output any bits. Which means that when I encoded my symbol with probability 1.0, it was encoded in 0 bits, which is sort of nice. That's sort of what I want, but also sort of weird and scary, because how am I able to send over data in 0 bits? It's sort of nice to learn that we're encoding symbols in 0.0001 bits, but it's really weird to be encoding things in 0 bits. It feels sort of like division by 0. I'm getting a little bit too close. The reason that it's valid is that it is actually true that the compressor is sending the decompressor a message in 0 bits. I'm actually giving the decompressor nothing, and the decompressor still gets my message. The decompressor still knows that I've sent it the escape symbol. Why? Well, because if the decompressor looks at this table, what symbol are you have to send it something. What are you going to send? There's only one thing you could possibly send. So you don't have to tell the decompressor anything for the decompressor to know that the first thing you're sending is the escape symbol. That's obvious from the distribution the decompressor starts with, which is sort of creepy, but also sort of cool, I think. The idea that we actually have gotten to the point where we can be reasoning about sending symbols in 0 bits. So yes, although we are sending it in 0 bits, and therefore in a sense it's sort of a notional encoding, no bits get generated, but the compressor and decompressor both know that there's only one outcome. It's a foregone conclusion. There's only one symbol that can appear, so the next symbol must be this. So it's not necessary for me to send you anything for you to know that. And so I don't send you anything because I don't want to waste your time. You and I both know the first symbol is the escape symbol, so I seamlessly generate 0 bits. What's also really cool about this is not only that I can encode things in 0 bits, but that it happens naturally as part of arithmetic coding. No extra work is needed on my part to implement that feature. It just happens naturally. So this symbol gets sent with 0 bits, and then I send over the A with probability 0.2. And the reason for this is because, again, the compressor and decompressor know that the first symbol has to be the escape symbol, so it's not necessary for them to say anything. They can do this without words. So what I want to talk about now is an example of applying this approach at a very large scale. So this idea, hopefully the last couple of examples, the fact that I could use multiple tables to take care of like the probabilities changing depending on what symbol I just saw, the idea of using an escape symbol to give the decompressor a hint about what I'm going to do next, and this observation that adaptive distributions seem to be quite helpful in working around some of the annoying aspects of arithmetic coding. What I want to do now is cover at least one, because we're about to depart from lossless compression. I want to cover at least one example, a detailed example of an adaptive technique, a modeling technique that applies these things in practice, not just a toy example using 2 tables or 3 tables. Although, of course, it's true that on assignment 4 or whatever, if you ever want to write some adaptive scheme, this is a valid scheme. It saves you bits. Why not use it? But there are much more complicated models in practice. I want to show off at least one of them as, I guess, some way of tying together the different threads I brought up in this lecture. So I'm going to talk about a technique called PPM, which stands for prediction by partial matching. And basically, it combines together the 2 previous techniques with a few extra layers of complexity. What it does is leverages this idea of using context and also using escape symbols as a way of telling the decompressor what it's doing at each step. Because we've maybe observed that if I keep seeing A followed by L, as I might do in sequences like this, then relative to A, if I know the previous character is A, the probability of seeing an L is pretty high. If I can arrange for both compressor and decompressor to keep track of that, and therefore encode L using its probability relative to other characters following A, I'll encode L with a high probability. And the higher the probability is, the fewer bits I need to use. And the way I'll do this is by basically keeping an accounting of previous patterns that I've seen. And with PPM, we use this notion of context of a certain length, a certain number of characters. So I could decide to keep track of all contexts of length 2. So AL followed by something, or SA followed by something, or LS followed by something. So I keep track of, for any 2-character sequence, the probabilities of characters I've already seen occurring after those 2 characters in the past. And with this idea that patterns tend to repeat themselves in longer sets of input, I could hope to get some leverage from this. In the event that a particular character hasn't been seen after, so suppose I want to see ALX, but I've never seen X after A and L before, I will also keep track of the single character contexts. So if a 2-character context is too specific, maybe I'll keep track of what characters I've seen after just L, or just A, or just S. And if even that is too specific, if I've never seen an X after an L, I will also keep track of what characters I've seen in general. So just the global probabilities of every character. And in fact, if I've never seen the letter X before at all, I'll even keep a fallback uniform distribution just like I was doing here. So I'll keep a whole bunch of different probability tables and switch between them at each step and tell the decompressor what I'm doing, and the decompressor can maintain all the same accounting I am. But by maintaining all of these different tables, I'm hoping to leverage, when a pattern occurs again, the benefits I get from keeping track of previous occurrences of that pattern. So PPM fundamentally relies on this idea of something called context. Now we know what context is, obviously. I'm going to use the term context in this case to refer to a thing. So when I said a minute ago, let's think about all the characters that have occurred after AL. If I'm encoding the current character and the previous 2 characters were AL, what I want to do is talk about the context AL, which is a table of probabilities of characters that have followed AL in the past. If AL is too specific a context, if I've never seen X in the context AL before, I will want to talk about the context L, which is a slightly shorter context and therefore maybe more general. If L is too specific, I will want to talk about the context empty string, which is to say, if I consider the previous 0 characters. So the idea in PPM of a context is a sequence of 0 or more characters of the input sequence that immediately precede the character you are currently encoding. And the distribution you use, so the distribution your arithmetic coder would use in PPM when you're actually encoding this symbol, is determined by the distribution of previously encoded characters within the same context. So if in the context AL, I have seen X 3 out of 5 times, and I have seen Y 2 out of 5 times, that I've previously seen the context AL, I would encode X with probability 3 over 5. So a few other examples of that, because the actual long example of PPM is pretty involved, so I want to set this up carefully. Suppose we're encoding this and we reach this. I'm encoding this character, this letter B. So the current symbol is the letter B, and the context, at least for our example, will be either ABC, or if that's too specific, BC, or if that's too specific, just C, or if that's too specific, the empty string, so 0 characters. There's a footnote. I don't really have very many of those in my slides anymore. We'll just go down and see what it says. Okay, the footnote says, yeah, right, the context can be longer than length 3. We're going to use length 3 because, as I mentioned in a previous video, the slides are of a finite width because YouTube does not yet support slides of infinite width. So I'm going to use length 3 because that's literally the maximum length I can fit in the slides, and even then it's a little bit dicey. So for every context string, so in the context of this B, I might actually have context tables stored for all 3 of these plus the empty string. For every context string up to some maximum, or actually not necessarily always a fixed constant maximum, but up to some maximum imposed by memory or recency or something else, PPM will maintain the frequency distribution of characters following any previous occurrence of that context string. And I'm going to visualize it like this, which isn't necessarily the ideal visualization, but I'm trying to work within the constraints imposed by the finite width of my slides. So to talk about previous occurrences of the context BC, so when I write the context table that I've drawn here is me saying every other time in this input sequence when I've seen the characters BC, I have observed the following probabilities for characters that could follow it. So that means I've only seen A, B, C, D, E after the characters B, C. There could be more symbols available, but I've only seen these 5. if I look at their total frequencies together, it adds to 48. I'm going to write that in the table with this notation as if it's a fraction, but actually the frequency really, of course, is just this. This is more correctly seen as the probability, but I'm going to call it a frequency for reasons that'll become clear in a few minutes, basically because I want this to be a number I can increment and this to be just the sum of all of the frequencies in the box. So that means that if I were to encode A in this context, I would encode it with a probability of 5 over 48. If I were to encode A in this context, so after the text ABC, I would encode it with 3 over 14. And so depending on how many context characters you have, how many you can use, I might use different probabilities. Now, I'm sure what you're wondering at this point is, I keep talking about different contexts. How do I know which context I'm allowed to use? If your previous 3 characters were ABC, you would default to this context, the most specific context available for the sequence you're working with. However, there are cases where that context isn't going to work. So what if the next character is D? Well, this context can't help you because there isn't currently a D available in this context. What we're going to do is provide some logic to say, I'm sorry, this context is too specific. I would like to jump backwards to a shorter context. I want to use the context BC instead. Notice how D can be encoded in that context. If not, I'd want to jump back to context C. So I need to give the decompressor a hint in this case. The decompressor will assume that I'm starting from the longest context available, so ABC. If I want to bail out, the decompressor has no way of knowing that I want to bail out in general. If I want to bail out, I have to have some way of sending it a message saying, sorry, this context is too specific, I want to bail out. If I have the symbol I want, so if I start in context ABC and I want to encode B, then I'm good. So we'll just encode B with the probability 5 over 14. After encoding B, after encoding anything in a particular context, so if I do ABC and then I see a B, I'll encode B with probability, I guess it was 5 over 14. Then I will go through and increment the frequency of B in all contexts that apply, all of them, not just the one I used. So I increment B here, I also increment B in context BC, and so that's this, and I increment B in context C, and even in the context corresponding to the empty string. Notice that when I do that incrementation, I'm incrementing the frequency of B, but I'm also incrementing the total frequency. Maybe now you can understand why I'm not actually storing this number as 5 over 48. I'm storing it as the frequency 5 and the total frequency 48, because then I can increment the total frequency very easily. And similarly, B becomes 6, and this becomes 15 in every case. I increment the total frequency here as well. So I'm just drawing it like a fraction. It's not actually being stored as a rational number or a decimal expansion. But then there's the question I alluded to earlier, which is, what if I'm in the situation where I want to encode D? Well, I can't do that because D isn't available in the context. I could do it if I could go backwards to the context BC, but I need to tell the decompressor what I'm doing. So the way that PPM handles this is by adding an escape symbol. So every context always has an escape symbol living inside of it with frequency 1. And just like before, that means over time, the escape symbol's influence declines, because as more and more symbols become available and their frequencies get incremented, 1 over 16 is going to be, or 1 over 16 is much smaller than 1 over 2 or whatever. So as more and more things show up, the probability of the escape symbol becomes lower and lower, which is good because as the context fills up, the likelihood that I'm going to need the escape symbol is going to decrease. So the idea behind the escape symbol is the decompressor will always assume that I'm in the longest context available. If I can't use that context, if I want to encode a D, I will send over the escape symbol as a way of telling the decompressor, I can't encode the next symbol yet, please jump to the previous context, so shorten the context by 1 character, and I'll try there. In this context, I can encode D, so I'll then encode D with probability 10 over 50, so 1 over 5. So in this example, because we want to keep things simple, I am going to, in every context, assume that the escape symbol has a fixed frequency of 1. It never changes. Now, actual PPM implementations may change that. So things are more complicated in actual versions of PPM because there are ways of optimizing it a little bit to save a few more bits. So one example is, if I only have 5 symbols, A, B, C, D, E, then after all 5 of them show up in a context, I can throw away the escape symbol. I'm never going to need it again. And I can save a little bit of bandwidth that way. We're going to have enough to deal with, so I'm not going to do that. But keep in mind, there are some optimizations that I am consciously not employing here because we just want to get through this example. So if the compressor is working inside of a context and it can't find the symbol it wants, it generates an escape symbol and jumps backwards. It'll keep jumping backwards until it finds the symbol it's looking for. So there are conceivably cases, if I wanted to generate ABCX, well then I have to generate an escape symbol to jump out of this. I jump backwards to BC, and I generate another escape symbol to jump out of that. I may have to generate, 3 or 4 escape symbols before I find the symbol that I want. Every escape symbol has a probability, and notice how generally those probabilities are low, which means generating escape symbols is pretty costly. But it's a worthy investment because over time, the probabilities of other symbols become high in a particular context, and that means that if I encounter those symbols, which do seem to be relatively common, obviously, I will be able to encode them with high probabilities. So really what I'm doing is ratcheting up the advantage I get from arithmetic coding here. Really uncommon symbols end up with extremely lousy probabilities because to encode them, I have to encode a whole bunch of escape symbols first, but really common symbols end up with really high probabilities. So I'm exaggerating the probability distinctions that arithmetic coding naturally is able to exploit. All right, so in the example with encoding D, I would generate an escape symbol to bail out of this context, and then I would encode D over here. And then, of course, once I've encoded the D, I increment the frequency of D in all contexts that apply. So even though I had to bail out of context ABC to encode the D, once I've encoded the D, I was still in this context, so I increment the frequency of D in all contexts that apply. So next time I encode a D, it will be available in this context. It will be available in this context to encode it directly with no escape symbols. Okay, so I would like to go through a long example of PPM. This is quite involved, and you'd be forgiven for having to watch this twice or stare at the slides for a while because I've had to diagram it out in a pretty messy looking way just to keep everything on the same slide. But I want to do a long example because I want to show off the advantages you can get over time. If I just did a short example that might be easier to draw, it wouldn't really be obvious where PPM is going, like what advantages we could get, so I really want that to be the case. So there are a huge number of variants of PPM. It's like the LZ family. There are tons of variants. They do all sorts of different things. I have tried to implement a very simple and very magnanimous one for this. So I'm not going to do any complicated optimizations, although in practice I probably would. I'm also going to use a very straightforward way of understanding context. I'll just have contexts of length 0, 1, 2, and 3, and then this special one that I'll talk about in a minute. Variants of PPM would often do things like maintain contexts of arbitrary lengths, but throw contexts away, so discard them if they haven't been used in a while. That's complicated. I won't worry about that. You can use your imagination. If you choose to implement PPM on assignment 4, when it's your choice what to do, you can get quite a few extra marks for implementing complicated. Even a basic PPM would get you quite a few extra marks. But implementing a very complicated PPM, you could clean up marks just with that. So the model I'm going to use here, if we wanted to talk about where it fell in the family tree, we'd probably call it part of the family called PPM3, which is PPM with 3 or fewer characters of context. There are versions of PPM that aren't constrained by a constant number of characters, but this one is. There are going to be at most 3 characters of context available. So what I'm going to do is I'm going to maintain context distributions for contexts of each length up to 3. So for example, I might draw a box in here where I maintain the context table for AB, which is of length 2. And the tables themselves will look sort of like these. So I've used the same format in both cases. And if I'm in context AB and I want to encode a particular symbol, so for example, I might see that in AB I'm allowed to encode symbols A, B, C, or escape symbol. What if I'm in context AB and I want to encode a D? Okay, well then I'm in trouble because there is no D here in this one, so I've got to jump backwards and look at maybe the context B. Okay, so what if I notice that in context B I've got A, B, C, and E, an escape symbol? Well, then I'm still in trouble because I can't encode the D. So I'll jump back to this context here, which will be the context corresponding to an empty string. But what if in the context for the empty string, I still have never seen a D before? So the context for the empty string only stores things you've actually seen. Context length 0 is, suppose I've seen a D and I want to encode it, and I've got no previous characters of context. But like any other context table, the context for the empty string will only actually contain characters that have previously been encoded. And so if D is still not available in my context of length 0, I need some fallback option. So like in the previous example with my uniform distribution, I will maintain a special fixed uniform context that I'm going to call the fallback context. I'll also write it as context left arrow because it's the context at the left-hand side. It isn't a true context, it's sort of a pseudo context. It's a way of encoding symbols that I have no other way to encode, a sort of context of last resort. So in this special fallback context, every symbol has the same frequency. Even the escape symbol, although you'll notice as we go forward, I actually could avoid giving this thing a frequency at all. I'll never need to bail out of context left arrow, so I could just leave the escape symbol off of that. But just to keep things consistent, we'll leave the escape symbol in. Okay, so at every step, the encoder and decoder, so if I have just processed characters A, B, and C, and I'm looking at the character D, both decompressor and compressor will begin by assuming that I am in context ABC. If I need to bail out, then I will have to tell the decompressor that I'm how many times I'm bailing out. So if I want to get to context BC, I generate an escape symbol. Context C, I generate an escape symbol, and so on. I'll always start with the longest possible context. So at the initial step, when I'm encoding the A, the context I'm in is going to be the empty string, which means I'm actually supposed to be in this context table here. Notice how this context table doesn't actually exist. I don't seem to have drawn it on the slide. This came up a couple of slides back. I want to make an observation about this now, but what I'm going to do, because we know that every context has an escape symbol by default, I'm going to not draw the escape symbol. So if you see a box that looks like this, where we've got A with frequency, let's say A has frequency 1 and B has frequency 1, I'm not going to explicitly draw the escape symbol in there because it would eat up too much space over time. We're going to assume that in every context, the escape symbol is always present and does have frequency 1. So you'll see a lot of contexts where I draw the frequency as being 1/3, even though it looks like there's only 2 of them there. It's because the escape symbol is silently sitting there with frequency 1. So it accounts for 1/3. Now, when I encode this first symbol, I'm supposed to be in the empty string context. But if I look in the empty string context, all that's there is the escape symbol with frequency 1/1. But both compressor and decompressor assume that I am at context length 0. So if I want to encode the letter A, I have to bail out of context length 0, the empty string context, by generating an escape symbol. Now that's pretty easy because the escape symbol has probability 1, so I just do that for free. But I do still notionally generate the escape symbol there. And then I generate the letter A with probability 1/7. So the total probability is then 1/7. Now, after I encode that escape symbol and then A, I occasionally call the escape symbol the empty symbol. Hopefully you figure out what I mean by that. After I encode escape symbol A, I then perform the update. So all the contexts that apply in this case, now of course because I just encoded A by itself at the beginning of the sequence, there's nothing else besides the empty context that I update. I will now update the empty string context with A with frequency 1. And you'll see, notice how it has frequency 1/2. That's because silently the escape symbol is assumed to always be there with frequency 1. Okay, so yeah, this is the slide pointing out that the escape symbol appears implicitly. Okay, so the next step, I'm encoding the space character here, and I'm starting from the initial context A. But I notice that if I'm encoding that space character, well, I mean, there is no context A, but really, in terms of what the decompressor and compressor actually read, when they look for context A, what they find is this context that has nothing in it but the escape symbol. So to bail out, because the context doesn't exist yet, I encode an escape symbol with probability 1. That brings me back into this context, the empty string context. So I'm now out of context A in the empty string context, but I don't have a space there either. So I have to generate an escape symbol to bail out of that into the fallback context. And that's why the context that I use is the fallback context. Now to bail out of this, remember that the escape symbol is sitting there with frequency 1/2. So that second escape symbol is generated with probability 1/2. Now I'm in the fallback context and I generate my space, it has probability 1 over 7. So I generated 3 things to output, to emit my space character, 2 escape symbols, and then the actual space. So I generated the first thing with probability 1, then 1/2, then 1 over 7. So the aggregate probability of generating this one character was then 1 over 14, just the product of all 3 of these probabilities. Okay, so I emit the 2 escape symbols, and then I use the fallback context, and then I perform my update. Oh, the update's here. So here's the update after emitting the space. I increment the frequency of space in my context table for length 0, the empty string context, and I add a context for A, which is the initial context I wanted to use, and increment the frequency of space there. Here is the slide I skipped over that just observes the process I just illustrated by hand, which is to generate that space, I had to send 3 symbols to the decompressor, which means, 2 of the symbols were just giving the decompressor directions about what I'm about to do. But if we're going to talk about the probability that I used to encode the space, I really should take these into account. I should take into account all the overhead associated with this character. So I had to step from a context of length 1 through a context of length 0, and then down into my fallback context, which I guess is sort of at length -1. I don't know what else to call that. And so the effective probability is the product of all 3 of these things, which is 1 over 14. And notice that because there was no context A, and a context not existing is sort of equivalent to the context just having the escape symbol in it with frequency 1. So that first escape symbol had probability 1 over 1, because both compressor and decompressor knew that that context does not yet exist. But really, we should view the symbol as being generated, even if it's sort of a notional encoding. All right, so we have to continue using the fallback context quite a bit early on. So when I encode the first S, my context is supposed to be A space. And if I look at my context table, I will observe there is no context A space yet, so I generate an escape symbol to jump back to context length 1. So I then look for context space, and that escape symbol had probability 1. I look at the context just space, but that's not there either. So I generate another escape symbol with probability 1 to jump backwards into my empty string context. And in my empty string context, there is no entry for the symbol S, so I have to generate another escape symbol, but this one shows up with probability 1 over 3. And that gets me back into my fallback context, and then I generate, I don't generate a space, I generate S. And so S gets generated with probability 1 over 7. That means the total probability is the product of all 4 of these things, which is basically 1/3 times 1/7, or 1 over 21, which isn't so good. That's a pretty low probability. It's lower than I would have if I used the basic adaptive model from earlier, certainly. On the other hand, I mentioned that the point of PPM and modeling like this is to ratchet up the advantages that arithmetic coding gives us for wide windows in exchange for ratcheting down, I guess, the efficiency for narrow windows. When a symbol has not occurred before or is very uncommon, we could end up with PPM encoding it with an extremely low probability. We're just hoping that on average, because common symbols occur more often, common symbols get more of an advantage, and therefore we get more of a compression benefit. It's the usual trade-off that we like to make when we're talking about valuing information fairly. All right, so we just encoded the S. We now update to increment the frequency of S everywhere that applies. In so doing, we've added a whole bunch of new contexts to our context tables. Notice how now there are 2 context tables available for length 1, the context space and the context A. Okay, we get to our second occurrence of A. So we are looking at this 4-character sequence, A space S followed by an A. Our initial context should therefore be A space S, but no surprise, there is no context A space S, so we interpret the context A space S as having nothing but the escape symbol, and we generate our first escape symbol with probability 1. That then gets us into contexts of length 2, but there is no context space S, so we generate another escape symbol with probability 1 and jump back over here. We now look at context S. Okay, well, still no, there is no context S, so we generate an escape symbol with probability 1 and end up back here. It's neat how in this example, on this step, all 3 of these escape symbols have probability 1, so none of them actually cost us anything. After all 3 escape symbols, we finally get to a context, the empty string context, where A is present. And then we therefore encode A with probability 1 over 4. So here we didn't need the fallback context. We finally were able to use some other context, even though it was the context of length 0. And maybe already you might be observing that if I had PPM and I didn't have these three contexts, so if I thought about PPM with only one level of context, I would actually have, or actually this would be PPM with zero, sorry, PPM with length zero or one level of context, I would actually have my very basic model from earlier with both the adaptive and uniform distributions, which is sort of neat. So in fact, we actually already saw a very basic PPM example. Okay, so after I do that, after I encode that A with probability 1 over 4, I go through and increment the frequency of A in all of the contexts that apply, and that requires finally creating a context of length 3. Okay, so now I'm encoding this letter D. So space SAD is my sequence, which means I'm using my initial context space SA. I don't have it, so I encode an escape symbol. I then try the context just SA, but I still don't have it, so I generate an escape symbol. I then jump backwards and try the context just A. I do have context A, but what I'm looking at is AD. And in context A, so in this context table, I don't have the symbol D, I just have a space. So I have no choice but to generate an escape symbol. In this case, the escape symbol will have probability 1/2. Because it's hidden inside this context table, but it is there. There is an escape symbol. That gets me back to here. I'm still sort of out of luck because there's no entry for D in this empty table either if I'm using a context of length 0. So I generate another escape symbol. The escape symbol in this table will have probability 1 over 5 because the total frequency is 5. So that's going to be 1 over 5. And then finally, I generate the D with probability 1 over 7. And so the effective probability of the encoding is 1 over 70, which is 1/2 times 1 over 5 times 1 over 7. So not great. But on the other hand, as usual, I'm banking on later seeing common symbols show up and get huge probabilities. And we will see that happen eventually. So I update my contexts. Now D is actually shown up, so I'll never need to go back to the fallback context for D again. I see another space character. In this case, I again generate 3 escape symbols because I want to be in context SAD, but that doesn't exist. I want to be in context AD too. It also doesn't exist. Context D doesn't exist. So I end up stuck back in the empty context, and so I generate space with probability 1 over 6 because all of these ended up being escape symbols with probability 1. So it didn't cost me too much, and the space is in the empty context. All right, so I add it back. I now try to encode a D here. So here I'm trying to encode D in context AD space. Can't do it, so I try just D space. I also can't do it. I try just space. Okay, well, I can use context space, but there's no D in it. My symbol is D. So I have to therefore encode this with 1. This is 1 out of 1. This is probability 1, 2. This would be probability. So to get out of this context here, the context space, I have to use probability 1/2. And then finally, I get back here and I encode D with probability 1 over 7. So my effective probability is now 1 over 14. Okay, well, that's tough luck. Okay, so I keep walking. I will skip through a few of these. I think you get the idea for these basic encodings. What I want to show off is as I go forward, how we are able to start generating things with huge probabilities, far greater than their global representation. If going forward you want a sort of estimate of the global probability of a symbol, the probability that a basic arithmetic coding algorithm like the one from the last lecture or the lecture before would use, look at this table. This table is a pretty good estimate of the global probability of a symbol, especially in the context of maybe a basic adaptive model like the one we used earlier. All right, so here I've got the initial context. I'm encoding, I'm going to encode space DA and then A. Okay, so I want to be in context space DA, but I can't. So I generate an escape symbol with 1 over 1. I jump backwards. I try just DA, still doesn't exist, so 1 over 1. I go backwards. I try looking for just context A, and I find it. There it is. And then I'm generating, oops, this is space DA. D, the symbol was D. My symbol is D, there it is, and I generate that with 1 over 3. So in this case, both escape symbols came for free, and I'm now generating D with probability 1 over 3. So despite the escape symbols, this is pretty big. if we consider that in our uniform distribution, it would be, what, 1 over 6 or 1 over 7. With a basic uniform model, it might be 1 over 6. With a true probability distribution, I don't think D would be even 1 over 3 in the true distribution. But because of the fact that D has occurred after A a couple of times before, I can predict pretty well that D might occur after A again. And so, therefore, I can generate D with probability 1 over 3. 1 over 3 is pretty good. When you've got more than 3 symbols, being able to generate anything with probability 1 over 3 is a pretty good deal. So I perform my update. I'm going to keep walking a few more steps and see a few more symbols. And I can see here, for example, I generate space with probability 1 over 4 because I'm able to start in context, oh, that's a weird one, semicolon space A and skip over context space A, but I end up back in context A. So just a single character context, which allows me to encode the space with 1 over 4. Instead of, currently its global probability is close to 1 over 4. Okay, so I'll keep walking, and then I get to this one. So this is a neat step here. Here I would like to try context space A space, but it doesn't exist. So I try context A space, and it does exist. It's actually this one. And the symbol I'm generating is S, which is already there. So I encode S with probability 1/2. And if I think about it, look at the global table here. So far in the sequence, I've seen 1 S. And that means that it's pretty unlikely that any model that just uses one character at a time would think of S as having a probability of 0.5. But because of context, because I keep seeing SA, I can benefit from the fact that I actually have that pattern already stored, and I can leverage context. I can encode it with probability 1/2. So these are the dividends I was talking about. All those times we were encoding symbols with probability of like 1 over 70, I was saying this will pay off, and here it is. I'm encoding something with probability 1/2. That's a 1-bit encoding if I'm using probability 0.5. All right, so I'll keep going. In this case, finally, I actually work with a 3-character context that already exists. So I've got A space SA. And I've already seen A space SA. And that means that when I encode A here, I'm actually encoding A directly with no escape symbols and probability 0.5. A's global probability is not 0.5. So here again, I'm seeing that benefit. And remember that a probability of 0.5 means I'm encoding this in 1 bit per symbol. All right, so I'll keep going. We'll see if we can find the next one of these. And again, here we go, encoding D with probability 0.5, 1 bit per symbol, even though D's global probability is not 0.5. And so as we're noticing these contexts fill up, we're getting more and more cases where we're encoding things with ridiculously high probabilities. There it is again, 1/2. Okay, and so here I encode an S with probability 1 over 10. That's a bit lower than S's global probability. And so we'll keep walking, and then we get to this. This is a huge deal. So here I'm encoding A after the context D space S. D space S doesn't exist, so I revert to space S, where A is already there. And I've seen so many space SAs so far that A in the context space S has probability 2 over 3. I am now encoding A in less than 1 bit, even though A's global probability is way less than 0.5. Okay, now here is a downside. So here I hit the very first L in my sequence. So I'm going to try to encode L in the context space SA. Okay, well there is a space SA, which means I have to escape from it using an escape symbol. Okay, the escape symbol is going to have probability 1 over 3 here. Okay, so I then try SA, but there's also a context SA, so I have to generate probability 1 over 3 for my escape symbol there too. So I try context A. Okay, well there is a context A, so I have to generate an escape symbol with probability 1 over 6. Okay, so I jump back here to my empty context, and the L is still not found there, so I now have to generate an escape symbol 1 over 20. Oh, this is getting pretty nasty. And then finally I go back to my fallback context and I use 1 over 7. So the aggregate probability is really awful, 1 over 7,500. On the other hand, that's because this is the first L. After this, I will at least have an L here. So the next time I encode an L, it won't be nearly this bad. And going forward, if my sequence is very long, I will amortize this pretty nasty cost over any other L's that I see. And if I never see an L again, who cares? I just encoded this one L with a nasty probability, but I don't have to worry about what the probability of any future L's is going to be. So that's a downside. And again, that's what happens if we exaggerate the advantages of using low or high probabilities, which really is what PPM is doing in a clever way. And then I encode an S with probability 1 over 7, which is breaking pretty much even. And then I keep walking and I get this. So right at the end, but this sequence could go on for a while. If I went through 1,000 characters with this, I would see this happen a lot. Right at the end when I encode that last A. So that last A is being encoded in the context ALS. But because we know L isn't very common, it shouldn't surprise us that ALS hasn't occurred before. LS certainly hasn't occurred before. But both ALS and LS give me escape symbols with probability 1. So they're actually free to generate. And they take me back to context S, which is this. And in context S, because A has followed S so often in this sequence, A has probability 3 over 4, which is 3 times its global probability, or almost 3 times its global, to be fair, almost 3 times its global probability, and 3 over 4 means I am encoding A in way less than 1 bit. That's a huge deal. And hopefully this example has been sufficient to maybe give you some insight into why PPM is a really effective technique in general. It's also very slow. A lot of work is needed on the part of the compressor and decompressor to keep track of all this data and curate the data, so to be able to actually find contexts and increment contexts and whatever. On the other hand, all of that is processor time or local memory. None of that goes in the bit stream, just these escape symbols, many of which are free. And when we encode symbols, we often are able to get these massive probabilities, which means we are encoding our symbols in significantly less than 1 bit apiece. Now, PPM is not the only probability modeling scheme that leverages context. It's one of many, but it's one that I could introduce enough to go through this complicated example that hopefully gives you some proof that this is a modeling technique that can pay huge dividends if it's used correctly. There's our last update, and then a couple of final points. So basically, the insight here is something that actually goes back to our coverage of LZW, which is what we're doing is trading processor time on the compressor and decompressor for saving bits. I don't send the decompressor that many extra bits. Instead, the decompressor does all this extra work. It duplicates my modeling. That's what LZW did. LZW had the decompressor duplicate the compressor logic. And in exchange, the decompressor didn't need the compressor to tell it what was in the symbol table. It could duplicate all of that information. We actually saw in lecture 4 a simple use of escape symbols. So we didn't use this on assignment 1, but in lecture 4 we noticed that the ancient Unix compress tool would allow the compressor to occasionally send the decompressor a reset marker to clear the symbol table. That's a way of sending the decompressor special directions that aren't part of the input sequence to synchronize the compressor and decompressor, to inform the decompressor of decisions that were made. So the key insight behind PPM is actually one of the insights behind LZW, a scheme that's much older than PPM and a great deal more primitive. So both escape symbols and this synchronization idea are things we've been seeing since the beginning of the course. Now, before I leave the topic, I should observe that, of course, there are tons and tons of things we could do to optimize PPM. A few obvious things I might think of based on what I just saw are maybe I don't want to store too many context entries, because if I want to have contexts of length like 10 or something, I'm going to have a whole ton of these tables, and that might eat up more memory than I have. Because as you can see, the number of tables sort of grows exponentially as I add to my length of my context. What I could do is put all the contexts in a priority queue and just delete contexts if I haven't used them in a long time. Because both compressor and decompressor could define common logic for how to do that, and they could both make the same deletions. It's true that by deleting a context, I lose all the advantages of using that context. It's also true that if I delete a context that is the prefix of a different context, I have to be careful what I do with the other. So if I delete this context here, that has an impact on whether I should keep these two. I might actually want to delete those as well. But using that logic would allow me to save some memory, and in turn maybe increase compression performance. The reason I would be increasing compression performance by that could include that I am allowed to use longer contexts because I'm saving memory, or also because maybe the context gets stale. Maybe if I haven't seen AD for a little while, maybe the fact that AD is often followed by a space isn't relevant anymore. Maybe that was only relevant 1,000 characters ago, so maybe I want to forget all of that contextual information. There are also quite a few different tricks you can use to avoid needing as many escape symbols, up to and including tweaking the frequencies assigned to escape symbols. As I said earlier, we don't need to do that today, but there are some pretty easy modifications, even a couple that I mentioned, that could be employed to save a few extra bits, to reduce our probabilities for escape symbols where they're not needed, and therefore free up a bit of probability space for other things. That is all something I'm afraid you'll have to work on your own if you want to use PPM in the future. I'm afraid you'll have to pursue that on your own time, because this course, as of the next lecture, is pivoting sharply, and we're going to start talking about lossy compression. After all this time of having to be perfect and keep track of every single bit, it's time that we allow ourselves to make mistakes. And even more so, if we're out of patience for compression, maybe we should start allow ourselves to begin throwing data away at will.